Hi, I'm Jeff Groh, and this is Differential Equations. Today we study the non-homogeneous case. These have the form x dot equals ax plus f of t, where f of t is not identically zero. Just as with the second-order linear, constant coefficient, ordinary differential equations, we will have two methods to solve these differential equations. First, the method of undetermined coefficients, and also a method called variation of parameters. This is going to sound a lot like what we did before. In fact, in presenting the undetermined coefficient case, I proceed by way of examples. We begin with x dot equals 3122x plus e to the 2t times 1, 3. The first step is, of course, to solve the corresponding homogeneous equation. And the first step in doing that is to find the eigenvalues. Here we have 3 minus lambda, 2 minus lambda, minus 2, and that simplifies as positive lambda squared. Negative 2 minus 3 is minus 5 lambda, and then 6 minus 2 is plus 4. You can see that we're going to have two negative signs here. Lambda minus 4, lambda minus 1. The eigenvalues are 1 and 4. If lambda equals 1, we subtract 1 from the diagonal elements, and we get an eigenvector 1, negative 2. This gives one solution, e to the t times 1, negative 2. If lambda is 4, we'll subtract 4 from the diagonal elements and get an eigenvector 1, 1. This gives a second solution to the homogeneous equation, 1, 1 times e to the 4t. With a homogeneous solution, c1 e to the t 1, negative 2 plus c2 e to the 4t 1, 1, we see that e to the 2t has nothing to do with the homogeneous solution. So in step 2, we are free to make the guess that a particular solution has the form e to the 2t times some vector v, where we know nothing about the vector v at this point. Taking the derivative, xp dot is going to be 2 e to the 2tv, and plugging that into the differential equation, we get 2 e to the 2tv equals, I'll denote the coefficient matrix by A, and then e to the 2tv plus e to the 2t times 1, 3. You can see that the factor e to the 2t can be canceled off. We'll move this term to the other side and this term here. This gives, inserting an identity matrix here, A minus 2i v equals minus 1 minus 3. When this comes to the other side, it switches signs in both coordinates. And when this comes over, we'll factor the v out on the right, just leaving 2i. This means that we have to subtract 2 from the diagonal elements and get negative 1, negative 3. In order to figure out the vector v, we need to solve this linear system. If we multiply through the second coordinate by a half and then move that to the first row, we'll have 1, 0, negative 3 halves. Multiplying the first row now by negative 1 and adding to the second row, we'll have 0, 1. Negative 1 times 3 halves is positive 3 halves, minus 1 is 1 half. With the vector v now known to be negative 3 halves 1 half, we have a particular solution of the form e to the 2t times negative 3 halves 1 half, and that gives the general solution x equal to e to the 2t negative 3 halves 1 half plus c1 e to the t 1 negative 2 plus c2 e to the 4t 1 1. With your experience in other cases for the method of undetermined coefficients, you should be able to solve other problems. For instance, in the last example, we had lambda equals 1 and lambda equals 4 with a forcing function involving e to the 2t. If the forcing function involved e to the 1t or e to the 4t, we would need to multiply by t to obtain something linearly dependent. From here we proceed to look at the method variation of parameters. As per usual, step 1 will be to obtain x1 and x2 as solutions to the corresponding homogeneous equation. If it is an n by n system, you'll need to go all the way up to x sub n. In step 2, the first thing we're going to do is form the fundamental matrix. The fundamental matrix is similar to the Wronskian in that it has these solutions down the diagonals, but the only thing it's lacking is a determinant. So it ends up being a matrix instead. Now, the homogeneous solution can be thought of as the fundamental matrix times a constant vector c. This would give you a linear combination of these solution vectors. We're going to assume that a particular solution is of the form x times some vector v, varying these parameters c. With a solution of the form xv, we'll calculate the derivative. By the product rule, we get x dot v plus x v dot. Think about the entries in this matrix derivative here. The first column is going to be the derivative of one of our homogeneous solutions, and the second column will be yet another. Since x1 and x2 are homogeneous solutions, x1 dot is ax1, and x2 dot is ax2. Since a is a factor on each of these columns, we can factor this a out and get a times xv equals, plus xv dot. In order for xp to be a solution to the differential equation, this has to be axp plus f of t. Well, xv is xp. And so in order for x dot to be equal to all of this, we need for this and this to match. Since xv dot must be the forcing function f of t, we deduce that v dot is x inverse times f of t. To get rid of the derivative here, we need to integrate. And then our solution xp, which we know to be the fundamental matrix x times v, is going to be x times the integral of x inverse f of t dt. That's important enough that I'll codify that as a theorem. We have the following. A particular solution of these non-homogeneous linear systems will be the fundamental matrix times the integral, the inverse of the fundamental matrix times the forcing function dt. You need to remember this formula. Since we're going to be calculating the inverses of matrices, suppose I have a matrix A, B, C, D. I claim that the inverse is 1 over AD minus BC, switch the diagonal elements, and negate the off-diagonal elements. This is my claim. We can prove the claim as follows. We can take ABCD and multiply it by this proposed inverse. This is a scalar, and scalars commute with everything, so we can just bring it out front. When we multiply, we'll have AD and then minus BC. Here we'll have minus AB, and down here we'll have plus AB for a grand total of 0. Over here we'll have CD and then minus CD for a total of nothing. And then, taking this here, we'll have AD and then minus BC. By multiplying each of these coordinates by 1 over AD minus BC, we obtain the identity matrix, and that proves the claim. As an example, suppose we have x dot equals 2, negative 3, 1, negative 2x plus e to the 2t times 1, 2. All of this is the forcing function. Now, step 1 is, of course, to solve the corresponding homogeneous equation. So we'll set 0 equal to 2 minus lambda minus 3, 1, minus 2 minus lambda. This gives us lambda squared minus 4, since it's a difference of square sort of product, and then plus 3. That simplifies to lambda squared minus 1, and hence the eigenvalues are plus or minus 1. If lambda is equal to 1, we subtract 1 from the diagonal elements, and we get an eigenvector equal to 3, 1. If lambda is equal to negative 1, we subtract negative 1 or add 1 to the diagonal elements. And we get an eigenvector 1, 1. We have a homogeneous solution then, C1 e to the t 3, 1 plus C2 e to the minus t times 1, 1. We also have a fundamental matrix equal to 3 e to the t, that's multiplying these, and then e to the t, and also e to the minus t, e to the minus t, multiplying each of these coordinates here. Calculating the inverse, we have 1 over, well, we have to multiply e to the t times e to the negative t. You add the exponents, that gives you e to the 0, which is 1, times 3. And then you subtract the product the other way. You switch the diagonal elements and negate the off-diagonal elements. So we have a factor of 1/2 out front. The next step is to calculate x inverse times f. So we're going to have 1/2 times this matrix, e to the negative t, negative e to the negative t, negative e to the t, 3e to the t, and the forcing function had e to the 2t times the vector 1, 2. That's going to be e to the 2t, 2, e to the 2t. Performing the product, the 1/2 is just a scalar coming along for the ride right now. We multiply row times column over here. E to the negative t times e to the 2t is e to the t. And then we're going to have negative 2 e to the t. So we'll have a positive e to the t and a negative 2 e to the t, giving us negative e to the 1t. Multiplying down here, we'll get a negative e to the 3t when we multiply these exponents, plus 6 e to the 3t. That gives us 5 e to the 3t. That's going to be x inverse f. The next step is to integrate. When we integrate these, and by the way, we don't need the plus c's on these since those will only contribute to the homogeneous solution. Integrating, we have negative e to the t and 5/3 e to the 3t, no plus c. We obtain the particular solution by multiplying the fundamental matrix onto this last result. You recall that the fundamental matrix was 3 e to the t, e to the t, e to the minus t, e to the minus t. We're multiplying that by 1/2 negative e to the t, 5/3 e to the 3t. We have this 1/2 still floating around. We're going to have negative 2 plus 5/3 e to the 2t. If I multiply e to the t times e to the t, I'll have e to the 2t. And if I multiply e to the negative t times e to the 3t, I'll have e to the 2t. So that's 5/3 minus 3. 3 is 9/3, so we have negative 9/3 plus 5/3 is negative 4/3 e to the 2t. In the last coordinate, we'll have a negative e to the 2t and a 5/3 e to the 2t. Negative is negative 3/3 plus 5/3 is 2/3 e to the 2t. Multiplying each of the coordinates by half and factoring out e to the 2t, we'll have e to the 2t times negative 2/3 positive 1/3. We see then that the general solution is the particular solution plus the homogeneous solution. The particular solution we just found is e to the 2t times negative 2/3 1/3 e to the t times 3 1 plus c2 e to the minus t times 1 1. For another example, let's suppose x dot is negative 2, negative 5, 1x plus e to the t times 1, 2. Of course, the first step is to solve the corresponding homogeneous equation, and to do that, we need to find the eigenvectors and eigenvalues. So, subtracting lambda from the diagonal elements, taking a determinant and setting it equal to 0, we have negative 2 minus lambda, 1 minus lambda, and then minus 10. We'll have a positive lambda squared, a positive 2 lambda minus lambda is plus 1 lambda. And then minus 2 minus 10 is minus 12. This factors as lambda plus 4, lambda minus 3. We have opposite signs and the larger one wins. This gives us eigenvalues of negative 4 and positive 3. For lambda equals negative 4, we add 4 to the diagonal elements. And since the coefficients here are the same but opposite signs, we get an eigenvector of 1, 1. For lambda equals 3, we subtract 3 from the diagonal elements. This gives us an eigenvector of 2, negative 5. We'll have a homogeneous solution of C1 e to the negative 4t 1, 1 plus C2 e to the 3t 2 minus 5. Given our homogeneous solution, we write down the fundamental matrix e to the minus 4t, e to the minus 4t, and then 2 e to the 3t negative 5 e to the 3t. To find x inverse, that's going to be 1 over negative 5 e to the negative t, and then we subtract 2 e to the negative t, switch the diagonal elements, and negate the off-diagonal elements. Out front here, we have a negative 7 e to the negative t. We're going to push the negative and the e to the negative t through, but leave the 1/7 out. There's no point in unnecessarily introducing fractions too early. Pushing the negative through will make every entry negative except for the one on the lower right. Pushing the e to the negative t through adds t to each of the exponents. So we're going to have positive 5 e to the 4t, positive 2 e to the 4t, positive e to the negative 3t, and then negative e to the negative 3t. Our next step is to find x inverse f. That's going to be 1/7 5 e to the 4t, 2 e to the 4t, e to the minus 3t, minus e to the minus 3t, and now the forcing function, which, if you'll recall, is e to the t, 2 e to the t. Multiplying, we have this 1/7. We'll have 5 e to the 5t plus 4 e to the 5t makes 9 e to the 5t. We then have e to the negative 2t and negative 2 e to the negative 2t making negative e to the negative 2t. Integrating, we'll have 1/7 times 9/5 e to the 5t, and negative negative is positive 1/2 e to the negative 2t. We then construct our particular solution by calculating x times the integral of x inverse f. Recall that the fundamental matrix was e to the negative 4t, e to the negative 4t, 2 e to the 3t, negative 5 e to the 3t. We're going to multiply by this 1/7, 9/5 e to the 5t, 1/2 e to the negative 2t. Performing the matrix multiplication, we'll have an e to the t out of all of this. Here's 9/5 plus 1, also e to the t. 9/5 plus 1. 1 is 5/5. 5/5 and 9/5 is 14/5 e to the t. Then we get 9/5 e to the t and -5/2. So let's calculate this. We had 9/5 minus 5/2 e to the t. That's going to be 18 minus 25. The answer will be negative. 18 minus 25. What is that? Minus 7/10. Multiplying through by 1/7 and factoring the e to the t out, we'll have 2/5 and -1/10. We have then the general solution. E to the t, 2/5, -1, plus c1, e to the 4t times 1/1, plus c2, e to the minus 3t times 2, -5. This last example is rather characteristic of these sorts of problems. You should study it carefully.